Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 6 of electronics. My name is Engineer Jaffar and I'm instructor for this course. So let's start with the recapitulation of the previous topic. In the last class, actually, we have discussed about transistors. That what are transistors? We learned about how you can use two junctions of PN. You can use either PNP or you can use either NPM. So you have to use these kind of semiconductor devices or materials which will have uh, I will write it down for you. So you will have to adjust or put n in between two p's, or you have to put one p, that is positively charged majority charged carriers element or device in between two negatively charged or electron majority carrier devices or elements. So these kind of arrangements, when you do, you have created just two junctions. One is known as this junction and this is your second junction. Similarly, here is the first junction in the NPN and here is the second junction for your NPN. So when you do such kind of methodology, you apply such kind of methods, you are getting a transistor, and a transistor has a three leg. It is a three-leg device. You can see that this is leg 1, this is the leg 2, and this is the leg 3, and these legs are termed as the emitter, collector, and base. And we are talking about a kind of transistor that is known as BJT. You know that transistor is basically classified into two types. One is basically BJT, and another one is FET, that is field effect transistor, and that field effect transistor is further classified into JFET, that is junction field effect transistor, and other one is MOSFET, that is metal oxide semiconductor field effect transistor. Similarly, this MOSFET is further divided into two classes, that is enhancement mode and depletion mode, and these are basically further divided into N channel and P channel enhancement mode. And similarly, this depletion mode is also classified into N channel and P channel as well. So a transistor can be of N channel with D MOSFET. Similarly, a transistor can be of P channel with E mode of, that is enhancement mode of MOSFET. Similarly, JFET can be classified into two types only, that is N channel and P channel. And the topic that we are going to learn today, and I already discussed it about in the previous class, is basically BJT. And this BJT is commonly divided into two parts. One is NPN and the second one is PNP. You can see that there are two major classes or classifications, and we are discussing about these two types, that is NPN and PNP. So in NPN or PNP, or you can see in BJT, we have three electrodes or three terminals. The first one is basically emitter. The second one is base, that is actually controlling, and we saw in the last class that how this thing controls the output current or the voltage to the load. And the last thing basically collector. So keeping that point in mind, let's start today's lecture. So I have told you that transistor is basically a control device that you can actually use it for control purposes. And I already told you that what is a control in terms of electrical terminology. When you use electrical terminology, control means two things, and remember that in mind. We will discuss that further inshallah in higher semesters as well. Control mean either to switch, it means either you can on or you can off any device or any load. Similarly, you can use amplifier. you can control as an amplifier, and it means you can increase the gain like a fan. You want to increase the speed of fan, you can increase the fan, increase the speed of the fan, or you can say RPM of the fan. Similarly, you can decrease it also. So if you want to change the amplitude of any given quantity, current, voltage, RPM, frequency, you can use amplifier. And if you want to completely turn it off or on, you can use a switch. But both these terms lies in the definition of control. So today, and we also discussed that a transistor is basically a control device. So it means it can do all of these stuff. The control means the switch and amplifier. And if I say that transistor is a control device, it means it can do both of these things. It can either switch these devices on and off. And we have discussed in the last class about an output characteristic graph, that how you can actually, this is your off mode, now this is amplifier, and this is your turned on. When the saturation is reached, it is basically turned on. So this is your on. Before that, this point it was off, or you can say cutoff region was there, or switch off region. And this is basically your amplification. You can say that you are increasing, or you can decrease as well using a transistor. So we will focus our class today in these two modes, that is a saturation mode where the device is completely turned on, or you can divide, or you can make it off. So we will deploy ourselves, or we will concentrate on these topics, on this area, that is where you have the switch on and off. Today's class. Excuse me guys, my throat is not working properly right now. I might need an amplifier. So if you can make me an amplifier, I will really appreciate that as well. So transistor as a switch, I've also discussed that what is a switch. So when you use an AC signal amplifier, the transistor base actually is that thing that is controlling everything. And in which way? In a way that this voltage applied at the base is applied in such a way that it is always operates in active mode, active region. So that is the linear part of the output characteristic graph for you. So I've already told you this is your output characteristic graph, and I had discussed it earlier that how you can use that. You have to make the mode active. You have to put your transistor into active mode. So that is where you can use this as a switch. However, NPN and PNP both uses bipolar transistors, and these can be made to operate as on-off type solid switches by biasing the transistor differently to that of a signal amplifier. So if you are receiving a signal, let me tell you how this definition works. If you are getting a signal, so by just allowing it, you can make it on. If your transistor is, let's say, I have discussed in the previous class that in NPN the base emitter junction is forward bias, and the base collector junction is reverse bias. Similarly, if you are you are using PNP, so your base emitter will be forward bias, and your common emitter, your collector emitter will be in reverse bias. So that will be your NPN working. So similarly, if you use forward biasing, so you will allow this current, you will allow this signal. So this will make your signal to go into the switch on mode, that your signal will be, your diode will be closed loop, acting as a closed circuit. So it will be allowing the current, so it will make the switch on. And similarly, if you do the reverse biasing, I mean that where you are applying the forward bias, now you are applying reverse bias, or vice versa. It means that if you have applied reverse bias earlier, now you are applying forward bias, so it will make your transistor to go into the cutoff region, that is switch off region, where the devices are open circuited, and the connection is de-established. So you lost the establishment of the connection, so where from where you can get no current at all. So that is where your off state comes, that is your cutoff state. And at that state the transistor will act as an open switch. You know that there are two kinds of switch. One is open switch, which do not allow the current to pass, and there is a closed switch. So if you use transistor with the specifications that I provided you the last time, uh, okay, sorry, close switch, it was close. So if you use your transistor with the class specifications that I provided in the last class, so you can use it as an on switch. That means it will be a closed circuit. And if you want to use that as a off switch, you can use that using this reverse, just by changing the biasing of the transistor that I discussed with you in the last class. So you can actually make the switch open and it will turn off the load. So this is known as transistor as a load. You can see that this diagram is your output characteristic diagram, and this region is basically switched on. You can see that after this region, this is basically the 90% of the first final value. Let's say this is your final value, and this is 90%. After you have received the 90%, the thing will be termed as switch on. Most of people ask that the switch is completely on here, so why do we have to mention this here, this point? Because the reason is two things: that you have to draw your cutoff line. You can see that this is the cutoff region, this straight line. You have to find the Q point, that is quality point. So, and I will discuss you that what is quality point, but for now just remember that you have to draw the characteristics of voltage versus current. And after the final value, after the you have received 90% of the final value, the switch is termed as on, generally on. So this is by convention, that if you have, let's say your final value was 100, this 100 was your final value, and if you have reached 90 value, the value of 90, so after 90, this thing will be termed as on. So from this point, this, or from this time actually, let's say this was 1 and this point was 2. So after you have received this 1 point and you know that this is approximately 90% of the final value, so you can term this as turn on switch. So this is basically a characteristic diagram that is showing you the relationship between the voltage and the showing you the current, output current versus the output voltage. So you see that as much you increase final voltage, your current gets increases, but at some time when the switch is completely on, it doesn't matter how much you increase the voltage, because if you increase the voltage further, the current will be constant because it has gone into a saturation region. And you know that saturation means by increasing the voltage you cannot further increase the current, because this is the maximum limit. And if you want to create to enhance more voltage to get more current, in the end you will left with nothing. The transistor will be burst and you will see nothing except smokes. So I prefer you not to do that. Do look at the data sheet before actually providing higher voltage to any transistor or any device. You have to look about the maximum voltage that that device or that component, electrical component, can receive, and do not go beyond that limit, because it will definitely create trouble for yourself and for that device as well. So moving swiftly on, some more explanation of transistor as a switch. So the areas of operation for a transistor are known as saturation region and the cutoff region. As I have already told you that these two regions where you terms this transistor as a switch is basically a saturation region, and this region is basically known as switch on region, where your device is completely on. This is your switch on region, and there is a region known as switch off region, or you can say cutoff region. There is a device where your device is completely switched off. So these are the two technical names for switch on and switch off. In switch on mode, and the device or the transistor have reached its saturation region. I will tell you, see, I will show you the diagram that this point, beyond this point, it has reached its saturation region. So after that point, your device will be turned on. Similarly, if your device is beyond the amplification region, you can say this point, very much low, less than 0.7 voltage you have applied in the VBE, so your device will be turned off because 0.7 will be neglected or dropped by the diode itself, that PN junction by itself. So I prefer you to apply low voltage and input when you want to your transistor to be in a switch off mode. So I have already told you I am going forward, I am going ahead of the slides. I am sorry for that. This is basically, you see that way, if you want to apply you want to your transistor to be switched off, you apply actually less voltage, less than 0.7 voltage at the VB, that is base voltage. So if you apply less voltage, the 0.7, because you know that this is your transistor, and the amount the voltage between this base and emitter is 0.7, because this is PN junction and the PN junction drops 0.7 volt. So if you apply less than 0.7 volt at VBE, automatically you are closing the switch, because this will be not sufficient for this junction to be broken. So from there you can have IC, the current will be equal to 0, because you are not allowing any current to pass through it. So that is where you have achieved your cutoff region, or your off mode. Your thing will be switched off. And this is the diagram that is showing you that how you can achieve that actually by putting a variable resistance as a input. So if you increase this Rn value, most of the current will be going here, and a lot of the voltage will be dropping here, resulting less voltage supplied here. So if you do such kind of stuff, you can see that there will be no current flowing through the device. So the resistors will be switched fully off, and there will be no current flowing from this VCC to the this emitter, from this current to the emitter. So your transistor is basically switched off. The second region is basically known as saturation region, and you have to apply much voltage and the input. You can see that the transistor will be biased so that the maximum amount of base current is applied. I've already told you have to increase the value of the base current so that you have to open this depletion region, or you have to minimize the depletion region so that the maximum current follows this way. Similarly, if the maximum current follows this way, more current will be coming in this direction, and we have discussed that in the previous class, that how this thing actually works. So this using this hierarchy or methodology, you can achieve this saturation region. Now coming towards the practical example, that how you can use the switch transistor as a switch. So using the transistor values from the previous tutorials, we have discussed about different numericals in the previous class as well, but now we will look at these as a perspective of a switch, the transistor. Using the previous values, where the beta, that was the transfer gain, actually the transfer characteristics, I've already told you that beta is equal to IC divided by IB. So if you have the beta, the value of beta is equal to 200, and the output current, that is the collector current, is given you 4 ampere current, and the base current is 20. So you have to find the base resistance, and you have to apply simply KVL, and using a KVL, I will tell you that how this is applied. So this was something like this. current, this was the voltage dropped at the resistor, and there was some voltage that is dropped, that is mostly 0.7 across VBE, and this was equal to the voltage supplied. So you can see now that this is equation of KVL, that the voltage rise is equal to voltage drop. So there was one rise and there was two drops. One was across the resistor and one was because of the PN junction, that is 0.7. So one rise is equal to the sum of two drops, and now if you rearrange this equation to find the value of RB, you can easily get this equation. And once you get this equation, you can easily put the value of these different variables so that are given to you already. So the value of V in is basically, you see that is 2.5 volts, and this value you already know that this is 0.7 because this is a junction, and junction drops 0.7 volt in a silicon or a germanium device, and this IB is given to you is 20 micro ampere. So you can see that 20 and 10 power minus 6, actually this is micro, so 10 power minus 6, and you have asked to find the value of resistance that limits the current up to 4 milliampere, and the base current should be 20, and the voltage supplied should be maximum of 2.5. So how much resistance? Because I have told you that using this resistor, actually you can actually control the switch as a open or switch. So it means that the value of the RB is of really great importance. So how you can find the value of RB? By using this equation, you can easily find the value of this RB, and it turns out to be 90k. It means that if you want your transistor to be act as a switch on device, you will have to put the value of RB equal to 90 kilo ohm. And after we put the value of 90 kilo ohm, it means that the maximum input terminal voltage will not exceed 2.5 volt, and the base current will be 20 microampere. It will do the reverse process as well, because if you are coming from this side, same will be happening other way around. So if you have reached the value of 90 degree, it means that the current was 20 microampere milliampere microampere, and your voltage was 2.5 volts. So this 90 kilo ohm resistor will be placed, you can see that over here on this side. This is your Rn, but this was RB in the numerical. So if you put 90 kilo ohm here, let me show you, let me label it. Actually, if you put 90 kilo ohm resistor over here, you can actually getting this circuit as a switch on circuit. Now coming towards different applications, you know that I've already discussed that how you can use transistor and different as in different areas of your life. Basically this is switch, and you know that what is the power of switch. Before these kind of switches, there was magnetic switches where you have to actually apply some a personal force or human force to turn on off or turn on the switch. Now you can use that easily by tapping a mobile screen, and you know the power of semiconductor devices. Already we have discussed about the applications of semiconductor devices or semiconductor materials, that how they are cheap and they are powerful. So using these kind of switches instead of mechanical switches or electromechanical switches that will be used, but I'm not telling you that these are completely replaceable with the high quality magnetic or electromagnetic switches, but they have their own importance. But mostly people are shifting towards high quality transistor switches as well. So maybe in coming 5 to 10 years or after 15 years, there won't be any mechanical switches, and there will be only this transistor which will be acting as a switch on or switch off. And you know that this is very good approach, but mostly these transistors are used for low voltages, or you can say low power devices. So in future we will be seeing, inshallah, some good transistors that will be working finely on some high power devices as well. So That's all for today. If you have any questions regarding the operation of a transistor as a switch or any previous topic as well, so you are welcome to ask. I will be very happy if you ask me questions, because you know that I love uh, if students ask me good questions. I also give marks to good questions uh, in terms of class participation. So it means that you are actively listening to my lecture. So I look forward to have your good questions in the class. And if there is any problem and you are not able to join the class because of some internet issue or any other commitment that is much more important to this class, I know that there are some reasons that you might not be able to. If you are not able to come to the class, there must be a solid reason. And if there is, so you are don't worry, you can also put your questions or your confusions on my email as well, or you can put that on through portal, or you have my number, you can easily message me to ask those questions on my WhatsApp. So I will be really happy if you ask me more questions, because you know that the more you ask, the more you learn. I'll be seeing you in the class, inshallah. That's all for today. Thank you. Allah Hafiz.